Today, we're going to peel back the steel and concrete on the world around us. We're going to reveal a hidden secret, a kind of superpower that engineers use to see forces that are completely invisible.
It's a totally fair question. You stand next to one of these massive structures, and it almost feels like it's just defying gravity. But of course it's not. And the secret to how it stays standing is what we're going to get into today. See, the thing is, every single beam, every column is in a constant, silent battle. It's this invisible tug of war with forces trying to squeeze it, stretch it, and tear it apart. And understanding that internal fight, well, that's the key to all of modern engineering.
So how in the world do engineers see these invisible forces? Well, they've developed a kind of superpower. It's like having structural X-ray vision that lets them peer right inside any material. This superpower has a name. It's called the method of sections. Now, that might sound a little complicated, but the idea behind it is actually beautiful in its simplicity. It's really just a thought experiment that makes the invisible visible.
Here's how this thought experiment works in basically 3 steps. First, you just mentally isolate the piece you want to look at. Then, and this is the cool part, you imagine making a clean slice right through it. Now, if the structure isn't falling down, that means something must be holding those 2 cut pieces together, right? The final step is to reveal and calculate exactly what those internal forces are.
And what's so cool is that when we make that imaginary cut, we pretty much always find the same 3 key players, the main characters in this whole structural drama. So let's meet them. First up, you've got the normal force. This is your classic squeeze and stretch force. It acts straight out from or perpendicular to our imaginary cut. If it's pulling the material apart, we call that tension. If it's squishing it together, that's compression. Simple as that. Next, we have the shear force. Now, this one doesn't pull or push, it slices. It acts parallel to our cut, trying to make one face of the material slide right past the other one, just like a pair of scissors cutting through paper. And finally, we get to the bending moment. And honestly, for a lot of structures, this is the big one. This is the snapping force. It's a twisting, rotating force that's trying to bend the beam. If you've ever snapped a twig over your knee, yep, you were creating a bending moment. Okay, so we've met our 3 forces, but here's where it gets really interesting. Their strength isn't the same everywhere along a beam. They change. They tell a story of stress from one end to the other. And engineers, well, they've learned to tell that story with graphs. You see, it's not enough to know the forces at just one spot. To build something that's actually safe, an engineer has to know the value of that slicing force and that snapping force at every single point along the way. That's how they find the one spot, the single point of maximum stress, the place where it's most likely to break. So what they do is they plot these forces on what are called shear and moment diagrams. You can think of these graphs as kind of the secret playbook for how a structure is going to behave. Let's take a look at a really simple example to see how they work. All right, this is a shear diagram. It's plotting that slicing force along the beam's length. So notice how from point A to point B, the shear is just chugging along at a constant positive 2.5 kilonewtons. But then, bam! Right at point B, this 5 kilonewton force pushes down, and the shear instantly jumps down to negative 2.5. And that jump you see, that illustrates a fundamental rule. The graph will always jump like that wherever a single concentrated force is applied. That visual leap is a direct signature of a real physical force pushing or pulling on that beam. Now, the moment diagram, which maps that snapping force, it tells a related but very different story. It's not flat at all, it's a triangle. The bending moment starts at 0, it climbs in a straight line to a maximum, and then it goes back down to 0. And here's the crucial link. The value of the moment at any point is just the total accumulated area of the shear diagram up to that point. Okay, so now we've got this whole story told in 2 different graphs. And this leads us to the single most important question for any engineer looking at this. Where is this thing's most dangerous breaking point?
The answer, believe it or not, is hidden in plain sight, right there in the diagrams. This is the moment where these abstract graphs become a concrete blueprint for how to design something that's safe and also efficient.
Here it is. This is the critical principle that connects everything. The point where the shear force is zero, the exact spot where that shear diagram crosses the center line, that pinpoints the location of the maximum bending moment. That's the spot. That's the place that demands all our attention.
And that's the whole payoff. The peak on that moment diagram, it identifies the beam's single most vulnerable point. It's where that snapping force is at its absolute highest. If this beam is going to fail, it's going to fail right there.
And once you get this, you start seeing it everywhere in the real world. I mean, look at big bridge girders next time you drive over one. They are almost always deeper, thicker, and stronger near the supports, exactly where the bending moments are highest. Then they can get thinner to safe material where the forces are lower. Or take a look at the shop crane. See that super reinforced joint? That is not some random design choice. It's placed there because the moment diagram proved that's the point of maximum bending. The physical shape is a direct response to those invisible forces.
So, in the end, these diagrams are so much more than just lines on a graph. They're a blueprint for strength. They tell engineers exactly where to put material, and just as important, where they can take it away. In the most beautiful designs, the physical shape you see is literally following the shape of the forces you do.
So the next time you cross a bridge, or you see a construction crane swinging overhead, you'll know the secret. You'll understand that hidden world of tension, shear, and bending that's constantly at play. Now that you can see the invisible, what are you going to look at differently?